but introduce Frédéric Brechenmacher, who's from the École Polytechnique and will be speaking this morning on mathematical fictions and mathematicians' choices.
Thanks very much, Joe. So actually, it's the first time we meet in person with Judd Open, which is quite unbelievable, I think, and which highlights how this conference is so nice and to either meet or see you all again. So thanks to the organizer, Adrian, of course, for all his work, and Chris, June, Troy, and of course, thanks to I. And so now it's my turn to reflect about this refrain of what I think the most significant open question or lacuna. And actually, I will follow Karen's lead and keep my opinion for the conclusion of my talk, partly for the sake of suspense, but also because maybe I will get some inspiration during the next hour. Anyway, this talk will have something to do with a slightly different question, which is actually what do practitioners of mathematics consider as significant? And I think that most of us have already experienced. I mean, mathematicians, they usually have a very strong idea of what they consider as significant. And here there's a huge issue, which I think is at least twofold. The one is the reception of research in the history of mathematics by mathematicians. And this is already something Karen just talked about in her talk. And sometimes it's very puzzling to how mathematicians can read our own work according to what they consider as significant. And my experience as an editor of a journal of history of mathematics for like 6 years, asking mathematicians to, work as experts, peer reviewers, is how often they would respond, oh yes, but I mean, this paper, this theorem is insignificant. And so there's the job of explaining what is significant maybe on this insignificant theorem in this history of this theorem. So it's a tricky issue, and I think actually it's very interesting, in this program to make explicit, especially for mathematicians, what we historians are considering as significant in our work. So that's the first thing. The other one is, of course, in researchers in the history or sociology of mathematics. It's, of course, difficult to work in this area if you do not have any idea of the values and hierarchies and who is the pandits among your actors. And of course, there's many things you can investigate, like prizes, awards, medals, journals, institutions, and so on. And it's a huge issue, and actually it has been discussed several times already this week. Already, the first talk by Nicola, we have seen how Whiteside, for instance, his idea of what is significant in Newton, the impact it had on the edition of Newton's work. And also in Karin's, of course, talk, the idea that the history of symbolism has to do with Viet algebra. Again, the impact it had on the historiography of symbolism. And Sayuri's work on statistics, the issue of what is significant in a collection of data and, of course, statistical function you're going to use. Then you have political issues, actually. And in the opposite, in Caroline's talk, the claim that actually there is only one significant method in, computing tables for life insurance. So this is huge, of course, and I'm not going to be able to deal with this issue just by myself. And so my actual issue is a bit narrower, is how do mathematical texts may express an intention of the writer, or maybe more precisely, a choice. What choices do we have in the history of mathematics of the choices that are expressed by practitioners of mathematics in different times and social spaces? So I will leave aside reflexive discourses about mathematics, like reports, eulogies, and philosophy and history of mathematics and so on, because of course, in this text, you have a lot of reflexive discourses of what is significant and the choice that is made by this mathematician and so on and so on. But my issue is really actual mathematical production, and especially papers. Is there any trace of choices that are made according to what one may consider as significant or insignificant? So, of course, then one could think about looking for how mathematicians use the term choice. And actually, it's quite easy because now we have like digital libraries of journals and so on, and you can just like go fishing for choices of mathematicians. But unfortunately, this term choice, it quickly became standardized with the development of mathematical journals in the 19th century. And so what is chosen is, it can be, the axis, the origin, the coordinates, the units, particular function, the value of a parameter. And the choice can be indifferent, convenient, skillful, of course, because you can simplify your equation. But it's a bit boring, Its choosing is often arbitrary. And according to, like, for instance, mathematicians of the Bourbaki group, the best is when you do not choose anything because you're there dealing with intrinsic stuff. So it's tricky, to investigate traces of the expression of an intention, a choice in mathematical activities. But there is one branch of mathematics, and actually that's what, that's why actually I got interested in this issue, in which expressing an intention or a choice is explicit, and it's something that is even considered as the duty of the mathematician, and that is descriptive geometry, and more precisely model drawing. So, as you know, descriptive geometry was formalized in the 18th century, into the variety of graphical techniques of engineers and artisans in the long run. And it was taught mainly by drawing, model drawing, in the long run, from the 18th to the late 20th century. And the drawings, they are épures, and so the action of épurer, it means that you remove insignificant elements. So you want to keep only what is significant. So here it's explicit, and in this history you can see, in this development, a form of mathematization that participated to the emergence of mathematical modelization in the long run, with very strong ideals of precision and clarity, which are not the same as the one of objectivity that you can find in other fields connected to the mathematical sciences. Because the duty of the drawer is to choose a point of view, what is significant and what is insignificant, which is the opposite of being objective. So we can quote, for instance, Carlo Bourlet in his inaugural lecture as a new professor of descriptive geometry at the Conservatoire National des Arts et Métiers in 1906. One should never forget that the unique purpose of descriptive geometry is to represent pieces of stones, of woods, of machines, of architectural details with the precision and clarity required for any effective achievement. The role, and I shall even say the duty, of the drawer is to represent objects in a simple manner. He cannot choose randomly between projection planes or even modes of representations, but has to be very judicious in his choices. He has to make see, and therefore being able to see by himself. So in this field, you have, explicitly the issue and even the duty to make choice. And how do you learn how to make choice? You have to learn to be able to see by yourself. Okay, but then how do you learn how to see by yourself? And that's a bit sad, because the way you're going to learn how to see by yourself, you cannot learn that in a textbook. You cannot learn that in a lecture by a professor. You have to practice drawing, and more precisely, model drawing. And there's nothing to say about that. And this is very clear already in the 18th century, especially in Monge, for instance, in his instruction for the teaching at the foundation of École Polytechnique. So the students, they have to draw. And actually, during the whole 19th century, 60% of the time at École Polytechnique, the students, they were drawing in the petite salle, like groups of 10 students without any professor, model drawing. And there is nothing to say about that. The exact description of the knowledge the student has acquired is the drawing. Okay. So how do you learn how to make choices? You have no written sources. The sources you have is the models and the épure. Okay. And this is very clear already, of course, in the 18th century, in the philosophy of Jean-Jacques Rousseau, which was so influential in the foundations of École Polytechnique and other grandes écoles in France. Crucial pedagogical issue in model drawing is to train the exactness of eye and the flexibility of hand. And this is considered as a preliminary to the faculties of both observation and judgment. And this is, of course, preliminary to the teaching of geometry. And of course, if you do not have a faculty of judgment, you cannot make choices. So you have to learn that. But you cannot learn that by attending to lectures of professors or reading a textbook. You have to practice drawing, and there's nothing else to say about that. So no written sources, actually. So you have traces of mathematical activities, but no, I mean, you have discussions about it, but yeah, nothing to write about it in a way. So, I mean, if you want to know how exact is your eye, I mean, if maybe your eye and your hand are properly trained, you can wonder, what is it? So this is an épure, but what does it represent? Come on. It's the eye and eye. So, yeah, it's not so easy, as you can see, or not see, actually. So it's the common volume between two toruses. It was made by Joseph Caron at the École Normale Supérieure in 1897. And this épure is very famous because Henri Lebesgue commented on it, because he had to do it as a student, and I mean, it was a pain. So we have these traces of activity, and we also have the models, of course. And then you can wonder how flexible is your hand. I mean, starting with these models, can you draw this? And you can see that, I mean, if you want to draw this with this, you're going to have to make choices. And you're going, maybe afterward, you're going to see these models differently. Okay? And your hand is also going to be trained a little bit. So another question, can you see what this is? It's better drawn, it's Gaspard Monge. I mean, so can you see what it is?
Gears.
Gears, yeah, no, it's not gears, come on.
Gears for turning right angle.
Yeah, gears right angle, I mean, almost good, but it's no gearings, of course, it's an épure of gearings. It's a drawing of gearings. So it's really exactly the same as an magnet. So, and that's the point of my introduction. I mean, so you have this issue that you have to make choice to select what is significant, épuré, and in the end, you get a picture, a drawing, and this is la trahison des images. It's a fiction. So that's actually how came to this topic of the issue of mathematical fiction in order to investigate traces of choices made by mathematicians. Okay. So now fiction. So mathematical fictions, they've used to be quite often an analytical category, especially in epistemological approaches to the history of mathematics, that has focused on the issue of the ontology of mathematical objects. And so you have a series of iconic fictions: irrationals, negatives, imaginary, infinitesimals, ideals, non-Euclidean geometries, and so on. And so, I mean, there's many papers about that, especially in the philosophy of mathematics. And just one example is a paper by Vincent Julien, Les fictions des mathématiques du XVIIe siècle restent à mi-chemin, in which Vincent Julien is making a clear cut in the history of mathematics between two time periods, one without fictions and the other with fictions. So without fiction is before the 17th century, so basically, to make it short, mathematics is considered as a natural science, Platonic vision of mathematics, so you don't have fictions. And then, starting in the 16th and 17th century, you're going to have like objects which raise ontological issues, such as imaginary numbers, infinitesimals, attempts to prove Euclid's fifth postulate, and as Vincent Julien is writing it, the concept of mathematical truth begins to waver. Then, at the end of the 19th century, you have foundational approaches, of course, axiomatic definitions, for instance, of real numbers and so on. But in the 20th centuries, then you have paradoxes, and you can see that actually you can choose between various axiomatic systems. And so what eventually mathematics may be entirely fictional after all. And that's the third, actually, time period, which is implicit in Vincent Julien's work, is the beginning of the 21st century with the development of fictionalism in the philosophy of mathematics, which in a way considers that mathematics is all about fiction, but also changes the philosophy of fictions. So I'm not going to get into any detail about that, but I just wanted to highlight that as an analytical category, fiction is mainly aimed at focusing on ontological issues. As Vincent Julien phrased it, do infinitesimal quantities exist? The answer would make fiction disappear. So it's clear. Either it exists or it doesn't exist, and there is fiction only when it doesn't exist in a way. And it has been used to put together various things in a diversity of times and spaces, conjectures, hypotheses, numbers, algorithms, abstractions, truths, formalism, and so on. A diversity of things, but actually mostly in specific domains of, so to say, pure mathematics, algebra, number theory, calculus, and so on. And also there is a kind of linear vision of the development of mathematics supported by the idea of an expanding algebraic universe. You're adding like fictions, so like Galois extension of your algebraic universe, as David showed quite recently. So my issue is to wonder about fictions as used by practitioners of mathematics, similarly as what we've seen in the Epure. So as an actor category, not as an analytical category. So that's what I would like to focus on. And so I don't know if it's an emerging theme, but it's an already emerged theme since I discovered 2 days ago that David Rabouin has just published a paper, December 2024, that I read yesterday, free afternoon. That was great. And it's a really great paper. I mean, if you do not know what to do tonight, you should read it. In which he actually did the same thing. I mean, he investigated actor categories about fictions in relation with negatives in the 16th and 17th century. But fortunately, I will focus on the 19th and 20th century, so we will not have a quarrel of priority immediately. So my sources, so I try to do something a bit systematic. And so I looked into all the journals that are digitalized by NUMDAM in France. So you have 48 mathematical journals, starting with the Journal de l'École Polytechnique in 1794, going on with the Annales de Jargon and so on. And after the 1860s, so I added several of the review journals that were created after the 1860s and which are not in NUMDAM, so I had to do this on hand. So of course the Yarbour and the Bulletin des Sciences Mathématiques and so on. And after that, math reviews and archive. And also a selection of periodicals about mathematics, but like the Revue Générale des Sciences Pures et Appliquées, which is a kind of journal of popularization of mathematics, but addressed to other scientists, or science addressed to scientists. And also l'Enseignement Mathématique. So a few quantitative remarks on the long run. So first, fiction is quite rarely used. And it's more often used in review journals than in actual mathematical journals. For instance, if you look at math reviews, since 1940, you have 348 results over more than 3 million references. So it's not like mathematicians do not write about fictions all the time, of course. Surprising result is that it's almost exclusively used in fields of applied mathematics. Okay. So it's exactly the fields that are not considered in the usual epistemological history of these iconic fictions like imaginary numbers and so on. Also, there is a boom after the 1960s, even when you consider it in regard with, of course, the exponential increase of mathematical publication at the time. So I should have used a logarithm basis because you cannot even see what's going on before 1940. I mean, because there's this boom. And so I'm not going to discuss so much about what is going on after the 1960s, but just to make it short, there's 4 main uses of the term fiction since the 1960s. The first is the increasing popularity of the expression fact versus fiction, or the science and the fiction in the titles of publications. And this point I will get back to it later. The other is math applied to fiction. So it's very diverse. It can be, AI-generated novels or things like that, but it can be also, an algorithm to avoid spoilers in fan wikis of episodic fictions. I mean, things very useful. There's, of course, the debate between realism and fictionalism in the philosophy of mathematics at the turn of the 21st century, and eventually science fiction, which gets quite popular in the 1980s, but is really standardized. Like, for instance, a few years ago, it really seemed like science fiction to be able to translate automatically a text in a different language, was now, I mean, it's really science and this kind of thing. So now my method is that I'm going to focus on the time period 1860-1960, and the reason is we've seen that we have many references in review journal. So the 1860s is when you get the first review journals. And the 1960s is when you get this boom. So that something is happening. Okay, so I'm just looking this 100 of years, which is already a long run. And I shall first try to wonder about a kind of cartography of the uses of fictions during this time period. So it's mostly in applied math, as I said before. And after that, I will, if I have time, look at a little bit more closely at a few mathematical texts dealing with these more iconic mathematical fictions like irrationals and ideal factors. So to contrast what we're going to see about applied mathematics with these iconic mathematical fictions. So let's start. So the first example is review by Joseph Bertrand in 1873 of the works of Maxwell and Thomson on electromagnetism. So Joseph Bertrand is really in the process of becoming like a pandit of French science. So it's just 1 year before he will become Secrétaire Perpétuel of the Paris Academy of Science. And it's also 1 year before the foundation of the Cavendish Laboratory in Cambridge, in which both Maxwell and Thomson are going to play a key role. So, I mean, it's not like, nobody's talking about nobody. But Bertrand is not very convinced about Maxwell's work on electromagnetism. And so he says, to calculate the magnetic induction across the closed surface, the author assumes that magnetism is distributed in such a way that all the charge of Bower fluid, for example, remaining internal to the surface, that of the southern fluid is external to it. So I will be skimming these references, and of course I will not have the time to discuss what is a Bower fluid and so on. My focus will be on the use of fiction. Thus, transforming into reality the legitimate fiction when it is a question of the action at a distance of the concentration of fluids in 2 points called poles. Such boldness would be enough to remove all credibility from the demonstration. As it has been proved since then, I mean, of course, with Maxwell's theory, which is, a fiction. So, 2 comments. One, fiction can be legitimate. Okay, that's the first. And the other is that the discussion is about types of mathematization. It can be legitimate in fluid mechanics, but not legitimate in electromagnetism. Okay, that's the issue. But the fiction in itself is not something that is unreal or that would raise ontological issues. Okay. First example. Second example, a fiction is suitable. That's actually its main role. It's useful. And it's useful for what? To get differential equations. So this is Rado in 1868. We can first place the origin of the coordinates in one of the mobiles, which we then considered as a central body around which n planets move. This fiction is particularly suitable for systems that contain a body of preponderant mass, for example, the solar system. So of course it's legitimate as mathematization, and then thanks to that, you're going to have differential equations. That's what you want. Okay? So the fiction is something that is a mean of action. You're going to discuss if it's suitable or not, and at the end, you get the differential equation. Very often it's the opportunity to discuss the hypothesis, and especially the mathematical hypothesis you're going to make in domains such as physics. So this is Joseph Boussinesq in 1880. In the question of potential, the hypothesis of the continuity of matter has the effect of extending the potential to the whole mass without altering the value of gravity at each point. But there is in this way of proceeding a fiction that is important to see clearly. It consists in reasoning as if the action of two material points were governed by Newton's law down to the smallest distances. A hypothesis which, down to the out of continuity, would have the result of reducing to nothing those forces that we call pressures, tensions, tractions, and so on, and which are usually the most considerable. So you can see the issue. A fiction is something that is important to see. It's a mathematician that you make. You're making hypotheses, and so you get something. You get differential equations and so on. But there's something that you're going to miss. And like, for instance, these forces, which are not limited to Newton's laws, such as pressures, tensions, tractions, and so on. It can be, of course, the applications of statistics as well. It's not limited to physics or mechanics. So, for instance, this is in 1901. Mr. Codelier is operating arbitrarily in relating marriages to a single female generation, under the pretext that it is the same age as the average age of marriages. This is turning an arithmetic fiction, all averages are fiction, into an effective reality. We can see the danger of this reasoning when we see that more girls of 20 and a half years old are often married than actually exist in this country. So again, it's discussing mathematization that is given to, in this case, statistical situation on the average age of wedding of girls. And so very often we have this formulation turning a fiction into reality. Okay. But it's not so much about the ontology, it's really about the legitimacy of what you're doing. And it can be that fiction really turn into reality, sometimes. So this is the case, for instance, in this review by Bull of Paul Appel, it's a Traité de mécanique rationnelle. All problems relating to a continuous medium seem obviously to require the consideration of three-dimensional space, but one can, in thought, imagine continuous media having only two dimensions. That's a fiction, it's in your thought. Such would be, for example, the medium constituted by molecules subjected to remain on a plane. But this fiction becomes a reality in three-dimensional continuous media where all the particles originally have velocities parallel to a plane and where it is obvious by reason of symmetry that this parallelism has no reason to be altered. So what used to be a mathematical hypothesis, a fiction, can turn into a physical reality, sometimes. So to sum it up, so these mathematical fictions, they are usually, the term is usually used to develop a constructive criticism or debate over the variety of mathematization that may be given to a specific situation. So mathematical fiction usually, it's useful, provides differential equations, but the problem is that it's general. Some people may say abstract, okay? And then you have to discuss its legitimacy and the scope, of this mathematization. So there is a tension between both the generality and the usefulness of the mathematical fiction and the singularity of the situation you aim at describing. And so it's often the opportunity of discussing the boundaries between mathematics and other scientific domains, such as, for instance, of course, physics. So this is, for instance, Lorberg in 1887. The author observes that the potential of the forces exerted by R on delta is a purely mathematical fiction. It has no physical meaning because these electromotive forces do not behave as they do in a rigid system and so on. So it's not an ontological issue. It's just that you have to see clearly that this is a mathematical fiction. We're dealing with a physical situation, but okay, no big deal. It's just that's what you have to do. Charles Darwin, so of course he's not a naturalist, he's the grandson of Charles Darwin in the Cambridge Philosophical Society of 1953. The author studies the actual trajectories of fluid particles in certain motions of an implicit fluid. It's not easy to read, actually. It is shown for the first time, as far as the reviewer knows, that the concept of hydrodynamic mass is not a mathematical fiction, but a genuine physical phenomenon, and so on. And usually, this boundary work is going to be based on experiments, of course. So now you have a physical experiments that show that this concept is not just a mathematical fiction, it's actually a physical reality, and so on. So it can be also between theory and practice, with especially the specific needs of engineers. So here it's the Colonel Devet, it's about the noise of airplanes or aircraft. So it only gives rise to a series of detonations, obviously devoid of harmonics, it's discrete. To apply Fourier's theorem to a series of periodic detonations and to consider the noise produced as a resultant of certain number of sinusoidal sounds would be to take for reality the elegant fiction of a mathematician. One does not have the right to make fictitious companion play and interfere in such a way. So, in application, when you're really studying airplane, you're not going to apply Fourier analysis, but nonetheless, it's an elegant fiction of mathematician. So it's not something that raises ontological problems as such. So this is a list of mathematical fictions. It's not a complete list, exhaustive list. So it can be a frame of reference, Hertz waves, forces, material points, arithmetic mean, pendulums, errors of observation, and so on and so on. And this term, mathematical fictions, it becomes quite rare after the 1960s. And of course, it's the time of the emergence of the notion of mathematical model and modelization. And actually, this notion, they replace, in a way, the use of mathematical fiction. And of course, I mean, when you introduce mathematical model, you discuss about the legitimacy of your model, the limits, its generality, the equations that you're going to get, and so on. It's exactly what the people, I mean, the actors we've seen in this text were discussing in regard with mathematical fiction. But it endures into the increasing popularity in the 1960s of the expression facts and fictions in the titles of publications. And actually, when you have a paper that says the science and the fiction, or facts and fiction, usually it discusses the scope of the mathematization, the modelization that is given to a physical phenomenon. So this is an example, 1967. So now it's really about a geometric model, and the terminology of model is used as such, but still, it's still talking about fiction. If such fiction supports the imagination, it is only through the equations it suggests to us that it can find a place in a rigorous theory. That's the issue. And you can compare this with what we've seen in Tina's talk yesterday about the biologists who reacted to Reshevsky's modelization of the division of a cell by comparing it to the one of an eye drop. And they say, I mean, if I remember what, to conjure up in the imagination a system of differential equations. That's the issue. Okay, so you're going to get this fiction. But the fact to say that it's a fiction or that you're conjuring it in your imagination, it's not as such something that is bad or that raises ontological issues. That's how you discuss this, actually, these issues. So fictions, they're useful, but they're general. And that's what you talk about when you're using this term fiction. So reflexive comments about the legitimacy of the choice of a form of mathematization, its usefulness and generality in regard with the singularity of a situation. Okay. So, as said before, little ontological issues, and that's how you can say that there's something connected to a matter of choice. Okay. So this debate about the legitimacy of using this form of model, we would say mathematical model, or this other, it's an issue of choice. So actually, this has no physical reality. It's a mathematical fiction and so on, but it's going to provide me with differential equations. It's a way to express a choice that is made by the author of the text. So I would like to explore this further, and this is the second part of my investigation, with a more local approach to this tension between usefulness and generality on the one hand, and the singularity at stake when people are referring to mathematical fiction. But this time I shall focus on the more iconic objects of the usual historiography of fictions in mathematics, such as irrational and numbers and ideal factors. So, as I said before, I mean, most references to fictions are in the fields of, so to say, applied mathematics, but you have some, of course, in other fields, and it's the ones, I mean, a few of them on which I will focus now. So, the first example, and actually the main example, is also, I mean, the reason I chose it is because it's the one I know the best, Leopold Kronecker. And as Cédric Vergniaud showed us in 2019, in handwritten notes from several of his students that are kept at the University of Strasbourg, I mean, he found this reference, I mean, this quote by Kronecker that the results of algebra must be made as independent as possible of all fictions about the roots of equations. So here we really have the iconic, you know, object of mathematical fiction. The roots of equations, it can be imaginary number, it can be irrationals, okay. And these quotations come from the lecture on the foundation of the theory of algebraic magnitude in 1891. And this issue, the theory of algebraic magnitude, was first presented in 1881, so 10 years before, at the occasion of the Jubilee of Ernst Kummer in Berlin. And it was published quite soon, but in the published edition of his theory, there is no allusion to fiction. It's in the handwritten notes of students that you have this issue of fiction, and it's not developed. So you can wonder what it means, and that's actually what I'm going to try to do. There is this legacy of Kummer's ideal factor, which, I mean, this is a well-known part of the history of mathematics, were introduced in the context of the investigation of a proof of Fermat theorem, and especially the attempt to generalize the unicity of the decomposition of a number into prime factors to Gauss's integers. And Kummer so introduced these ideal factors as something that act on divisibility, but he could not materialize them as numbers. They didn't have the properties you would expect from numbers. And so he made an analogy with what was then designated as the hypothetic radicals in chemistry. So it's something that it cannot be isolated from a chemical compound, but it acts on the chemical properties on this compound. So it's the same thing. It's something that is in the numbers, and it acts on the properties of divisibility, factorization of these numbers. And Kronecker so wants to deal with the more general problem of the arithmetic of algebraic magnitudes, that is, magnitudes that are defined by polynomial equations. Polynomial equations, magnitude, we would say it's the roots of the equations, but without the fiction of the root. Okay. So, of course, I will not have the time to go deeply into Kronecker's Grundzüge, but just to remind you that so his theory is characterized by first a naturalistic conception of mathematics, which is common at the time, right? The idea that mathematics is natural science. But with Kronecker, I mean, it's the integers that are natural. So you're going to start with the integers, and you build on them. So we could say that's a kind of arithmetical foundation of algebra, and Kronecker would say it's an arithmetical, yeah, I mean, that's what he says. There's a principle, very strong principle, of effectiveness of computation. So you have the four operations of arithmetics, and you only have that, and you're going to use them a finite number of times. Okay. So no extraction of, for instance, square roots. It's only, you can add, subtract, multiply, and so on. And there's also a priority to operations in regard with objects. And that's why, so it's dealing with explicit polynomial formulas and no towering up abstract structures. And so it's very much opposed to Dedekind's contemporary approach which is based on abstract objects such as ideals, fields, and which requires non-effective procedures. And okay, so that's what Kronecker doesn't like, actually. So, maybe a short must be somewhere. So maybe, in short, so the issue is to classify, characterize the algebraic magnitudes that are defined by polynomial expressions, such as this one, for instance. Okay, and so here you can say, okay, it's just the square root of 2. But no, because this is a fiction, you know, of the roots. So you want to get rid of that. So it may seem a bit strange, but of course, what you can do as well is to look at the ring of polynomials on the rational integers, and to look at it modulo this irreducible polynomial, and you can work with that. And in a way, you're going to do the same thing as if you had this extension with square root of 2, but you don't have square root of 2. And that's the main issue, is that you want to get rid of it. So that's not exactly, of course, that's a fiction. I mean, that's not exactly what Kronecker does, because, I mean, it doesn't like objects such as principal rings, in a way. But when you're doing this, you're going to have, like, really polynomials, and you can work with these polynomials, and then you can wonder about, especially, how they can be factorized, what is the equivalent of prime numbers, irreducible polynomials, and so on. So about this issue of fiction, the way I look at it is with my background of knowledge of Kronecker. The first time, to my knowledge, when he expressed this issue of opposition between arithmetic and algebra, it was with his very strong controversy with Camille Jordan in 1874. And there was already this issue about the roots of the equation, and which he blamed as being purely formal, and that was the problem of the algebraic method, as opposed with the singularity of arithmetic. The fake generality of algebra, this is the singularity of arithmetics. So actually we find again this issue of the generality of something, the singularity of something else, but also the usefulness. Because algebra is useful, and Kronecker does not pretend that it's not useful. But the problem is that you have to discuss the legitimacy of this generality and usefulness in regard with the, as he says, the internal reasons of arithmetics. And that's what he said is at stake in this controversy. So very briefly, so it's about the determination of classes of equivalences of pairs of bilinear forms, like that. So you can express this like this, like a polynomial of bilinear forms, and then you get a matrix, we would say nowadays. And then you compute the polynomial, which is the characteristic equation, and it's of degree n in lambda. So you get n roots. I mean, if you believe in the fiction of roots, which is the case of Camille Jordan, unfortunately for him. And so he's characterizing the situation by what we would designate today as the Jordan canonical form. So here you have the roots. And if you have multiple roots, then you may not have a diagonal matrix, and you have Jordan blocks, as we would say nowadays, and so on. And so it works very well, but you need an algebraic closed field, because you need to be able to compute all the roots of the equation. And Kronecker, and to my knowledge, this is the first time that he is expressing it explicitly, is not happy with this. And for him, it's really bad mathematics in a way. What is important for him is to introduce what invariance, which can be computed effectively, and that's what we would call nowadays invariant factors. And we can compute them effectively as the weighted common divisors between the minors that are extracted from this determinant. So you do not have explicit formula anymore. So you lose the formula, but you have a procedure which is effective, that you can really compute arithmetically. And that's what Kronecker considers as suitable to the internal reasons of arithmetics. Whereas here you have the means of action of algebra, and it can be very useful. But for Kronecker, this is an arithmetical problem. I mean, come on, quadratic forms is Gauss, And bilinear forms, the generalization of quadratic forms, and it was introduced by Berliner mathematicians in the 1960s, like himself and Christopher. It's about arithmetic. So if you're using this kind of means of action, okay, maybe, well, but in the end, for the result, you have to find something which is arithmetic. And the problem is that if you need the algebraic roots of whatever polynomial, then it doesn't work anymore. So that's the opposition between the fiction of the roots and the internal reasons of arithmetic. So it's very briefly formulated, but in a way you can, my point is to focus on the fact that in Kroneker's fiction, you can see again this tension between usefulness and generality of the means of action of algebra, as he says. And he has nothing against that. I mean, you can use it. But in the end, you have to discuss its legitimacy with the singularity of what you are studying. And in this case, it's arithmetic. So, I mean, it's nonsense to just stop the investigation with a Jordan canonical form, because it doesn't mean anything arithmetically. So it's very similar to the use of fictions in applied mathematics. Usefulness, generality, versus the singularity of the situation. And so if you take seriously Kroneker's naturalistic position on mathematics, then we could consider that in a way, here you have a kind of modelization. The foundation, the arithmetical foundation of algebra, algebraic magnitude, can be understood as a model that you put on arithmetics. And that's Kroneker's one. It's effective and so on. But if you look at Dedekind's one, you could consider it as another model, exactly as when in applied mathematics you're going to discuss two forms of mathematization. So maybe that's something we don't want to do. I mean, to consider that, for instance, Dedekind's ideals and fields and so on, they're just a model, and exactly in the same sense as Kroneker's foundation of algebraic magnitudes. But that's what the term fiction is for. I mean, it says the same thing in the case of applied mathematics, what we would nowadays, consider as a model, and in the case of pure mathematics, like in the case of, Kroneker theory or Dedekind's one. So to formulate this a little bit differently, and so it's going to be a kind of fictional story about Kroneker. It's not real, but again, fiction, they're useful, so I'm going to use them, okay, to try to express something. So you have this issue of the fundamental theorem of arithmetic, decomposition to prime numbers, unicity, and so on. Okay, so 6 is 3 times 2, great. But then, of course, you can write this. And so, you lose the fundamental theorem of arithmetic. How is it possible? Because you don't have a unicity of decomposition anymore. And of course, it's the same with polynomials, the polynomials that Kroneker is interested in. So here you have irreducible polynomials, but you can go on. And the reason you can go on is to shift from a principal ring to an algebraic closed field. Okay. So if you consider the fiction of the roots of equation, then you can do that. And so you lose, you kill arithmetic. And so you cannot then develop the arithmetical foundation of algebraic magnitudes. You cannot do any arithmetic. You lose the fundamental theorem of arithmetic. And it's the same with polynomials and so on. While if you consider that you're going to have the quotient of the principal ring over an irreducible polynomial, you don't have this problem anymore. And my point is that, so this is, again, something that is at stake in the controversy between Kroneker and Jordan, and it can be considered as a matter of choice. Are you considering an algebraic closed field, as Jordan does, or the principal ring? So, conclusion. So, mathematical fictions, as we have seen, as an actor category. So first, there is little ontological issue regarding the existence of the objects under consideration. And the main issue is the usefulness and generality of a form of mathematization versus the singularity of a situation. So it can be seen as something that is going toward the notion of mathematical model, except that we can find it in pure mathematics as well. And here it's more about debating the choice of a point of view. so it's precisely what I'm interested in. Expressing an intention. So I want to use a principal ring and not an algebraic closed field, and it's my choice in a way. Again, it contrasts with the ideal of objectivity. So now I'm considering this terrible question, what I consider as the most significant open question in my area. So to me, I mean, what is significant in my area is the issue of articulating various scales of historical analysis between the micro and the macro levels of history. And if you remember Vincent Julien, so it was 2002, it's basically when I started the history of mathematics. And you still had these long-run global histories, like you could divide the history of mathematics in 2 time periods, with or without fictions. I mean, it's cute, I mean, it's so nice and so on. But unfortunately, we do not believe in it anymore for various reasons. One is that actually it was just fakely global, as we know, and Karen just talked about it, because of course there's the women and the African-American people and so on. So actually it was a fake global history. And the other reason, of course, is that we have now all this micro-level analysis which are documented by deep archive research and so on, and which have raised many other issues and so on. But then there is this issue of articulating the scales of analysis. And so what I find interesting in this issue about mathematical fiction is that it allows to make explicit some choices made by mathematicians in the long run, at a time when mathematics was still largely considered as natural sciences, and most mathematicians did not claim their own creativity or freedom of expressing an intention in their work. And so it's something in the long run, as we've seen, but we've seen also that it may shed a new light on micro-historical episodes. It's what I try to do with Kronecker, but there's many other ones, like Poincaré's conventionalism, and his famous sentence about the fictions of Riemann and Beltrami. But maybe the terminology of fiction should be understood a bit differently than it used to be. Same with Émile Borel's concern about foundational approaches, axiomatization, and the thing he blamed as the mathematician who is absorbed in his dream, and the pure fiction of absolute determinism. And what he did was to construct real numbers based on probability theory, and so he gets something that is faithful to Kronecker's principle of effectiveness in the end. But even Pierre Duhem's social interphenomena. So this very long-run idea of the interrelation between hypothesis and truth in science and the role of mathematics, and something that is very close to what we would designate as models, by the way. So what I find appealing with this issue is that so you can discuss it at various scales, and even larger scales than what I considered. For instance, in the 18th century, you have all this criticism about mathematics and more generally les systèmes, as fictions. And famously, for instance, Buffon or Diderot, they are blaming general systems, such as, for instance, Newton's mechanics, as fictions. You know. And you can see that in the 19th century, there's a very fine debate about that. So it's not anymore the opposition between like general theoretical system and the singularity of naturalist investigation. There's this debate of, okay, this is a bit general, but it's useful, and it's legitimate in this case, and so on. And at an even more global level, the issue of the fiction as means of action and something that has to do with generality. I think that if you look again at the classical, iconic mathematical fictions, you find this issue of generality all over the place. It's the case with Stiffel's approach to negatives, Descartes, imaginary, Leibniz, infinitesimals. I'm not a specialist, but David Rabon just published a very nice paper about that. And he shows that, so you have something in the 17th century which is in continuity with more ancient practices, such as the one of false position. And it seems to me that there is something in this mathematical fiction that, in a way, remains in the very long run at a global level, and that has still to be understood. And so you can maybe recall this fiction I did before. And so nowadays it would be, I mean, absurd, such as the controversy between Jordan and Kronecker. I mean, of course, you have two binary forms. You have to say in which domain the coefficients of the forms are. But how do you express this? You're going to say, for instance, let A be an element in a finite field, okay? Or if A is in Fp then, or as if A was an element of Fp. And when you're doing this, you're making a choice about the generality of what you're going to do. But how do you make this choice? And you do not express the choice you're making. But it's something that mathematicians are trained to do. And there is a very strong issue at stake, because if it's too general, you're going to kill the problem, exactly as Jordan with the issue that Kronecker is interested in. But if it's not general enough, you're not being able to solve your problem. Okay. And so it's a matter of choice, and there's this issue of this history of how mathematicians express their choices in mathematical projections, the traces that are left by such choices, and how mathematicians are trained to make choices. So thanks for your attention.
We've got 4 minutes and 11 seconds for questions. Troy?
Could you show us your slide? You have to go back a fair amount about your sources for the bit of
the sort of bibliographic work.
Yeah.
Right. So you've got at least 3 languages there: English, French, and German, right?
Well, it's going to be mostly French, because it's the ones that are digitalized by Numdan.
Okay.
But the thing is that since you get also the main review journals of the time, you get reviews of papers published in German or in English and so on. But it's focused on the French scene.
Okay. So are you sure that fiction and fiction mean the same thing? And what makes you choose just this one word, related words? And how might the semantics have changed over time? I guess what I'm asking is, if you were to broaden this and add those extra considerations in, do you think it would change the perspective at all?
No, I mean that's a very good question. Actually, that's something that I just put under the carpet. It's still a work in progress. I mean, of course. I mean, not only depending on the language, but also, I mean, the time and space. I mean, fiction can mean different things. And that's what I said before, that this issue of having this cartography of fiction. And it's also in the various languages of mathematics. But I mean, it's a bit tricky. And what I wanted to focus on is that, I mean, surprisingly, I mean, it's something really I didn't expect. You have one main use, which is the one I presented. So of course, it's not the only one. You always have, individuals who are doing something else. And there's something, I guess, that should be investigated further. I mean, you're right.
That's Sonia.
Right, it's a comment.
Speak as loudly as you can, because the people in the back may not be able to hear.
Okay, then I'll show you my back. It's a comment with a question together. The comment is, Vincent is not only fake global, he is simply wrong. And the question is, no, I mean...
In a fiction?
Yeah, about the fiction.
No, but that it is a fiction as well.
But the 17th century.
No, I think, at least what I understand of ancient and medieval mathematics is that mathematics is an abstraction, and the entire discipline is a fiction. And they talk about these objects they are talking about not as natural objects, but as objects of their imagination, right? So this entire thing.
So that's David's paper is really great about that, showing the long-term issue that Vincent Julien didn't see.
Right. So the question is, what's the difference between abstraction and fiction? Is there any?
That's a very good question as well. But most of the time they do not talk about abstraction, as you've seen. So mathematical fiction is really used in a quite specific issue, which is really usefulness, generality, and to discuss the singularity of the... So we could be tempted to use abstraction, but then there's the issue of the analytic category that we want to use. Is it a model? Is it abstraction? I don't know, but I think something that would be interesting is to compare with an investigation of how they use abstraction, actually. Yes.
We've got time for one more question. Michael.
Thanks, Frédéric. How confident are you about the periodical literature as a proxy across the periodization that you're interested in? Because, of course, the role of periodicals in mathematical communication, not to mention mathematical research, changes pretty drastically across especially the medium and longer durays that interest you?
Yeah, definitely. But that's the issue of articulating scales. I mean, you're absolutely right. That's an issue. And not only this one, but also you have heterogeneous sources. You have reviews, and you have actual papers, and this kind of source. And this is the usual problem with quantitative approaches, of course. And I don't have any, I mean, we have like theoretical works on these kind of issues, how you're going to articulate the micro level and the macro and so on. And it's an issue that has been raised already 100 years ago in the École des Annales and so on. But I don't have any specific theoretical solution. What I'm usually doing is what I've shown. I mean, kind of articulation between quantitative approaches and specific local investigation of, like for instance, Kronecker or other people.
Well, we've now overrun our allotted time, so let's all thank Frédéric once more.